Welcome to this part. In this part we will continue from where we have left in the last part. So last part we have completed the this counter, okay, 3-bit up down counter. Now we'll move on to the shift register counters. So shift register counters are nothing but the application of shift registers also. So just the shift registers are there, and then the shift registers are used as counters. So with the help of this shift registers, we can make two type of counters. So one is called ring counter and the other one is called the Johnson counter or the twisted ring counter. Why they are called so, we'll understand it. So in ring counter, you see, if you want to design a ring counter, so the arrangement is very simple for a ring counter. We don't have to do much, we have to just connect them as we connect them for a shift register. So we connect the flip-flops, we take the flip-flops, whatever flip-flops are given, and we connect them as we connect in a shift register. So in shift registers we connect them back to back. So J1 is the output of J1 goes to the input of J2, the output of J2 goes to the input of J3, becomes the input of J3, and the output of J3 of the input of the third flip-flop becomes the output of the third flip-flop becomes the input for the fourth flip-flop. And here the only change which we do is, like, the output of the fourth flip-flop is feedback to the is returned back to the becomes the output of the fourth flip-flop becomes the input to the first flip-flop. Okay, and similarly the output of this Q4 becomes the input, Q4 bar becomes the input to the K input of the first flip-flop. So this is why it is called ring counter, because we are connecting the output to the input again. Okay, so output of the last flip-flop is connected back, output of the MSB flip-flop is connected back to the input of the LSB flip-flop. Output of the MSB flip-flop is connected back to the, both the outputs of the MSB flip-flop are connected back to the respective inputs of the LSB flip-flops. Okay, so this is a very simple shift register counter. So the flip-flops are arranged as we have discussed. Then the Q output, okay, of each flip-flop is connected to the next flip-flop, and that means the last output is connected back to the first flip-flop. So the array of this flip-flops are arranged in a ring way, in a ring fashion. So that is why it is called a ring counter. So what happens when the first clock pulse, and you can see that it is a synchronous counter because all the clock pulses or all the flip-flops are getting the clock pulse, the same clock pulse, and they are all triggered simultaneously with a single clock pulse. So that is why it is called a synchronous ring counter. Okay, so synchronous counter and it is ring. Now when the first clock pulse appears, that time this Q1 sets to 1, whereas the other flip-flops Q2, Q3, Q4 are 0, 0, 0. So our first state will be, let's say, this 0, 0, 0, 1. Okay, so Q1 is 1, whereas the Q2, Q3 and Q4, all of them are 0, 0, 0. So we can say that this is our first state. Now after this state, what will happen? The counter will go into the next state. So what is our next state? Our next state will be, okay, don't assume this as Q1, whereas assume this as Q1. Okay, so your first state is this one. So Q1, Q2, Q3 and Q4. I have written it in the opposite order in this case. I must have written as we have written in our last slide. So that should be like uniform, but by mistake it is written. So you assume it like this. So this is our first state. Okay, so actually I have asked my this TA to prepare the PPT and he has done this particular thing. So okay, no problem, we will discuss it this way. So you see, this is our LSB. Okay, so this is our LSB we are considering here. So this is our Q1 and this is our Q4. So Q1 is this, and when the next, so the first clock pulse, the first state is this. So when the next clock pulse appears after the first clock pulse, so initially this flip-flop is in the Q1 is equal to 0. So the other outputs are 0, 0, 0 after each clock pulse. So when the first clock pulse comes, okay, so the counter moves into this state. So the next state, because this one which is on the LSB is shifted, so 1 bit shifted. So when this next pulse comes, so it this one, it shifts in the right direction, so it is a right shift. Okay, so now when the next pulse come, the second pulse come, then it shifts one more bit. So when the fourth pulse come, then it shifts one more bit. So you can see that the ring counter can count only these states. Oh, okay, where the one is shifting from one position, the one on the LSB is shifting, the one in the LSB position is shifting in the one, shifting by one position. So that is why what you can see. Okay, so this is your ring counter, and with appearance of every clock pulse, the output shifts one bit, one position. Okay, so shifts one bit right. So these are the only states which are possible in a ring counter. So you can see that in asynchronous counter, if we have used 4 flip-flops, we were able to count 2 to the power 4, that is 16 number of states. But if we use a ring counter, then we can only able to count this 4 states, okay, like this. So this is a misuse or the wastage of hardware. So this is what the problem with the ring counter which happens. Okay, so this sequence, so this is whatever we have written, Q1, Q2, Q3, Q4. So the same thing you can see it here as well. Okay, so Q1, Q2, Q3, Q4. After the clock pulse, after the first clock pulse, after the when there is no clock pulse, this is the initial state. After the first clock pulse, this appears. Okay, whatever I have shown you in the last state diagram, so that only you can see here. So this was our first state, then this is our second state, this is third state, this is fourth state. After fourth state, 0001, when the next clock pulse appears, the state again becomes the same, okay, as the first one, and it keeps on repeating, it keeps on counting this sequences only. There is you cannot count anything else from this ring counter. Okay, so this is what the thing is. So the number of flip-flops is equal to the mod of the ring counter. So if suppose you are said that it is a mod 3 ring counter, so it means that it can count only 3 states, it can go only in 3 states, and the number of flip-flops to make that ring counter will also be 3. Okay, if it is an mod n counter, so the number of flip-flops will be used to make that ring counter will be n. Okay, the connections will be same as I have shown you for mod 4 counter in this discussion. Okay, but it can be anything, the connections will be same, the only thing is the number of counts will change, okay, accordingly, but it is a lot of wastage of the hardware. So an n bit ring counter can only count n bits, whereas an n bit ripple counter can count up to, so this point I have already said you. Okay, so this is what happens. So ripple counter can count up to 2 to the power n number of bits, whereas n bit ring counter can only count n this bits. Okay, n counts. So and this number of counts which it can count, or the number of flip-flops which it have, is called the mod of the ring counter. You can verify the truth table of this flip-flop. So you can see of this counter that when the clock pulses appear, then what happens? Initially all of the counters or all of the flip-flops are in the 0 state. Okay, only the first flip-flop is in the 1 state, 1, whereas the other flip-flops are in the 0 state. When the appearance on the appearance of the first clock pulse, negative edge of the first clock pulse, this transits, whereas this also, so this is the negative edge of the first flip-flop, so this transits. When the negative edge of this flip-flop occurs, this transits. The negative edge of this flip-flop occurs, this transits. So you can see that the counter is moving in only 4 states. So this is 0 0, okay, so this is 0 0 0 1, then it is 0 0 1 0, then it is 0 1 0 0, and it is 1 0 0 0. Okay, so this is what the states, and again it comes in 0 0 0 state, and then it moves to the other states. Okay, so this is how you understand, and the advantages of ring counter is that it is very fast. Okay, so it can count very quickly, but the only problem is that there is a lot of wastage of the space. Okay, and it is uneconomical to realize the this particular ring counters, whereas you don't require any decoder to decode the outputs as you require in case of asynchronous counters, because if they are asynchronous counters, so we require decoders to decode the output, but here they can be directly decoded. Okay, now let's see the other counter, which is our twisted ring counter. So twisted ring counter is more or less as the ring counter. The only difference is, let's say the connections will be same. The only thing is, what we are doing is, rather than connecting, in the previous case we have connected the output of the Q4 to the input of the first flip-flop Jn. What we are doing here, okay, is like we are connecting the output from Q4 bar, the Q4 bar to J1 and Q4 to K1. Okay, so this is what the change is. Otherwise the circuit is same. Just by doing this modification, what we can do is now is like we can count number of states. We can increase the number of states in which this counter will go. Okay, otherwise it is also a shift register counter, but now the number of states which it can count is exactly double compared to the ring counter. So twisted ring counters can count 2n states compared to the n states which we can count by ring counter. Okay, so you see the states in which this counter will go will be starting from the 000. Okay, it will go into let's say it will go into, so you can see the states, it moves in this particular states. Okay, so 000, then 100, then 1100. So this we will see by the state table as well. So this is a counter which uses n flip-flop, but it goes into 2n states rather than n states as it was in case of ring counter. The Johnson counter or the twisted ring counter goes into 2n states. Okay, whereas the ring counter is called as the number of flip-flops which you use in a ring counter is also called its mod n counter. Okay, so if n number of flip-flops you are using in a ring counter, it will be called mod n counter, mod n ring counter. Whereas if you are using n counters, n flip-flops here, so if you are using n flip-flops in a twisted ring counter, then it will be called mod 2n counter because it will go into 2n states. That is what is called mod 2n counter. Okay, so the output of each stage, as I have told you already, that how it is connected, then therefore it is called your twisted ring counter. Okay, and this counter provides you serial in and serial output register. Okay, so this we know already. Then let's move on to the another states. So if you write the state table, so this state table looks like something like this. So sequence table or the truth table if you write, so what happens after every clock pulse, if the counter is in this state, then on the appearance of the first clock pulse it moves to this state, then on the appearance of the next clock pulse, so it moves on. So just by looking at the connections, you can see that the circuit moves into the various states. Okay, into this various states. So initially flip-flops is reset, we always assume, and after the clock pulse, after the first clock pulse, you can see that as the feedback is coming from not from the Q1 but the Q1 bar of the last flip-flop, that is why it is able to count 2n states, because then it will become 00, then rather than 1 will appear in between. Okay, so you see this what is happening. If this is our clock pulse, Q1 is becoming 1, okay, on the appearance of this flip-flop. So you can verify the operation of the circuit with the help of this timing diagram. So if you find any problem, you can ask me, we can solve this ring counter. Okay, so this problem, and I can verify this truth table view, but you just try it by your own, and I am very much sure you'll be able to do it. Okay, so this ripple counters are more economical compared to a ring counter, but still they are less economical than your ripple counters. And this are like not probably we do not use them, but for only for some particular applications we use them, otherwise they are not that much useful. So now after doing this, I expect you to solve these problems by your own and try them by your own. So design a mod 6 counter, synchronous mod 6 counter. So if you want to design a mod 6 counter, obviously you will require 3 flip-flops, as I can give you a hint here, but then there will be some unused states. So considering those unused states, decide the circuitry, because this is a synchronous counter, so it will not be same as the asynchronous counter. So decide the circuitry, the combinational circuit which you will require in between the first flip-flop and second flip-flop and the second flip-flop and the third flip-flop. So decide that and then complete the circuitry and do it by your own, and you can discuss this thing in the tutorial class as well. So the other question is design a type D synchronous counter. So type D means use a type D flip-flop. Okay, type D synchronous counter which counts this 4 states. So it should count 0, 1, 2, 4. Okay, it should skip state 3. Okay, and the undesired state must always go to 0 on the next clock pulse. So if it is coming in the undesired state, let's say 3 is the undesired state, so it should not go into the state 4 or state 2. It should go to the state 0, okay, on the appearance of the next clock pulse. So considering this situation also, okay, so you have two situations, so you design this problem as well. So here you know that the number of flip-flop, because the you require to design how many states, you need to design 0 1 2 3 4. Okay, so if it would have been up to 3, then you could have used 2 flip-flops, but as 4 is coming, so then you will require 3 flip-flops, not the 2 flip-flops, but you will require 3 flip-flops. And if you use 3 flip-flops, then there will be 4 number of unused states, because 4 states you are using, but a 3 flip-flop can count 8 states in total, 0 to 7. So apart from this 4, the remaining states, okay, 0 1 2 4, apart from 0 1 2 4, the remaining states, okay, 3 5 6 and 7 will be your unused states or invalid states. If the counter goes into this state, then you have to make the circuit such that it comes into the 0 state. Okay, so it should get resetted. So considering this, draw the state diagram, and then once you draw the state diagram, write the state transition table. After writing the state transition table, you have to use D flip-flop as it is written here. In the previous question, it was not mentioned which type of flip-flop you have to use. So in that case, you can use any flip-flop. But here, as it is mentioned that you have to use D flip-flop, so you use that D flip-flop only. And then after writing the state transition table, considering the invalid states, and for those invalid state don't care output, okay, then you design the circuit, okay, in between what is required between the two type of D flip-flops, 1 2 and 3, okay. So then you design, and once you complete this, show me in the tutorial class, okay, and then get logic diagram and verify it with the help of the timing diagram. So thank you for listening. Okay, so with this we complete this particular counters. Here in the next unit we'll start different topic. So thank you.